The subject of my talk is SCP-SLAM, Accelerating DynaSLAM with Standing Confidence Propagation. This is the outline of my talk. The first is the introduction on the background. Visual SLAM is widely used in many applications, such as virtual reality, autonomous vehicles, robotics, and so on. However, moving objects in the real world are great challenges of improving performance. Robust dynamic SLAM methods usually distinguish static and dynamic feature points. Then the dynamic feature points on moving objects are detected and eliminated. The static feature points are selected for camera pose tracking. There have been many dynamic SLAM methods, which can be classified into learning-based methods and geometry-based methods. The learning-based methods combine deep learning techniques with the SLAM framework, such as DynaSLAM, but requires a large amount of computation time. So how to accelerate dynamic SLAM methods? We know the geometry-based methods can detect and eliminate dynamic feature points quickly, such as epipolar constraint. However, these methods are not sensitive to small moving objects. Therefore, a way to perform dynamic SLAM effectively and efficiently is to combine learning-based and geometry-based methods. Next, we see some related work about dynamic SLAM. Firstly, learning-based methods are most with semantic segmentation, which can distinguish and track moving objects, such as mask fusion and DynaSLAM. In addition, DynaSLAM performs a motion consistency check to improve positioning accuracy. And detect SLAM uses the concept of moving probability to distinguish the DynaSLAM feature points. However, the methods all suffer from high computational cost. Then geometry-based methods use geometric information to distinguish static and dynamic feature points, such as refusion and epipolar constraint, and ransack use simple fundamental matrix to characterize dynamic feature points. However, these methods suffer from mismatching of feature points, resulting in wrong localization. So we need an effective and low time complexity method to deal with these problems. Next, I will give the details of our method. There are two modules that take RGBD images as input. They run in two parallel threads, namely the confidence thread and network thread. The standing confidence propagation module is used for propagate standing confidence through frames. It determines the states of feature points according to the residual derived from the rigid transformation between frames. The semantic segmentation module performs object detection and semantic segmentation using the CNN model on keyframes. Then the states of the feature points in each frame are determined by the standing confidence of the current frame and the semantic segmentation result of the keyframe closest to the current frame. The states of feature points in the current frame are then used to compute the standing confidence of the next frame. Standing confidence is the probability of a feature point belonging to non-moving objects. As the camera moves, the point position changes. If the point belongs to static regions, the position change is only caused by the camera motion in three-dimensional space. On the character, if the point belongs to moving objects, the change is caused by both the camera motion and the movement of the object itself. We can use different position changes to distinguish static and dynamic feature points. Two-dimensional and three-dimensional distance measure are used to calculate standing confidence. The two measurement results are normalized to 0 to 1. They are used to represent residuals caused by transformations between frames. The point state depend on both the measurement of the current state and the state estimation from the previous frame. Mask RCN implements object detection and semantic segmentation based on ResNet and the feature pyramid network. Although mask RCN can get accurate bounding box and mask results, it runs slowly. So our method runs the network only on keyframes and propagates standing confidence through other frames in parallel. Here, the picture shows the original image and the semantic segmentation result. White mask areas represent the moving objects, and green is a standing point. Red are dynamic points. Finally, we get the moving object ridges. Then we combine the standing confidence with the closest keyframe semantic mask to get the final result. Our method uses two threads to execute in parallel, corresponding to the network thread and the confidence thread. According to the final result, the dynamic feature points are eliminated and the remaining static feature points are used for tracking. Next, we show some experimental results. We have conducted experiments on the public TOM at born datasets and compared with other SOTA methods, which include DynaSLAM, refusion, mask fusion, and LCCLF. First, we compare the runtime of different methods. The results show that SCP-SLAM required much less computation time and was about 10 times faster than DynaSLAM. Then we compare the camera trajectory error measured by the absolute trajectory error and the relative pose error. We can see that SCP-SLAM had smaller errors than other methods. In addition, we also provided visualization results of camera trajectory errors. The blue represents closest to the ground truth. However, the red represents a large error. It can be seen that our method was much closer to the ground truth. There was an application of augmented reality. Some virtual box was placed relative to the position of the camera. This provides that our method got reliable camera tracking results in a dynamic environment. Finally, it is the conclusion. We have presented a standing confidence progression module, which is combined with the semantic segmentation module through thread parallel. The experimental results show that our method can significantly reduce the computation time without reducing the accuracy. As the future work, we plan to optimize the method to prefer streaming processing and applying to more applications.